Hello there, ATS EVS 533 students. Dr. John Schrage here, helping you review for the first exam in our class. Just to be clear about this, I made this review presentation without looking at the test. For that matter, I made the review sheet that is available to you on Blue Line without looking at the test. I probably made the test without looking at the review sheet or this presentation. Well, yeah, because the test already exists. All of them are expressions of what I consider to be important in the class, but I don't actually, I'm not telling you exactly what's on the test. I'm not telling you, not everything I'm telling you today is on the test. Not everything that's on the test is in this presentation, okay? Alright, so anyways, just so we understand each other about things like that. So basically in this lecture, this module of the course, we had 6 lectures that had content about how the course, for the course in there. We were labeled 1B through 1G for our 6 main lectures. And let's just kind of work through them one at a time. And what I'm going to do is just put examples of slides that we saw over here on the screen with us. And then there's a little bit of text on each one of these here. But that doesn't necessarily mean that's the only slide that's important. It just sort of is there to sort of jog your memory as, oh yeah, well, I remember when we were talking about that. Okay? So for example, from our first lecture that actually had content for the course, you probably remember that we talked about things like who established the Intergovernmental Panel on Climate Change. I mean, the IPCC is the author of the report that we're working through this semester, the 5th assessment report. Who is in charge of that organization? And for that matter, what is the purpose of that organization? What do they do? What don't they do? Etc. We had quite a few slides that had explicit quotes about the role and the importance and so on of the IPCC. And we also on that day started talking about the questions of what constitutes weather and what constitutes climate, which might not exactly be the biggest surprises for somebody who's studying environmental sciences or something like that. But I think that is something that decision makers and so on often need help understanding, is how weather and climate are different and how we use different tools to describe these different phenomena, and how, if you're a survivor of the 105 class, you learned about the different kinds of models that we use for weather versus climate and so on. But if not, we're going to talk about such things in kind of a brief way later in this semester. An important factor that we need to keep in mind when we're talking about weather and climate is to remember that climate is going to be largely described in terms of statistics. Now that was things like means and averages and so on, but it can also be the range of variability, it can be about trends and so on, but statistics are key to our understanding of climate. When we are working in this class, we're going to be using certain terms, and we need to make sure that we understand, we're going to get more technical later, but make sure you know about things like what do we mean by climate change? What do we mean by the word anthropogenic? For that matter, what is the difference between the greenhouse effect and the enhanced greenhouse effect? And for that matter, how does that all tie in together to this idea of global warming? Remember, those are all kind of nuanced. There's slight differences between what we mean by each of those terms, and if any of them are something you're not clear about, let's make sure that you are. I'm not terribly certain that I'm all that likely on the test to have a question about, what's the difference between the greenhouse effect and the enhanced greenhouse effect. I might. That doesn't sound like that exciting of a question, though. But on the other hand, if you use the terms wrong on the test, I don't really have a lot of choice except to take off points. So we want to make sure that we are clear about all these terms. Don't use the word global warming unless what you mean is global warming. When we were kind of setting up in lecture 1B how the course is going to work, one of the things we talked about is how we have multiple lines of evidence for climate change, and how that's actually very important to our understanding. How having multiple ways of coming up with the same conclusion is much more robust of a way. It's a way to have more confidence in our results than if it was all from the same line of evidence. Okay, if it was all just different ways of saying using the same data, or if different data sets were contradicting each other. That is not, though, in general, what we're going to see when we talk about climate change and when we examine the so-called climate change indicators. Now, make sure you know, I don't know that we had a dictionary definition of climate change indicators, but we went through and we saw that there were all these different ones in the atmosphere, and the cryosphere, and the hydrosphere, and on land surfaces and so on. There were different processes, different epiphenomena that we can be measuring, like lower atmospheric temperature, upper atmospheric temperature, length of glaciers, sea level height, all these different phenomena that are indications of when climate is changing. We also talked at this point in the course about the business of temperature anomalies. Anomaly is an important vocabulary word in science in general, and it's important to understand what an anomaly is, how are these anomalies computed, how are different kinds of anomalies computed. Well, we mainly were working with them like anomalies in the sense of with respect to a reference value, where the reference value is actually the 30-year average of temperature at that location, or pressure at that location, or whatever the quantity is you're looking at here. So like here we had an example of temperature anomalies. Could you look at this plot and tell me what does it mean that someplace is red? What does it mean if something is blue here? Does that mean it was cold there? Does that mean it was colder than normal there? Things like that. Okay? And that kind of got us to the end of Lecture 1B, which brings us into Lecture 1C. Now, Lecture 1C is a little bit of kind of a dumping ground of a whole bunch of topics. We started off by talking about different trace gases in the atmosphere, and how, in particular, we're interested in certain greenhouse gases, the gases that are enhancing the greenhouse effect, and we looked at these, like, obviously, we tend to care the most about carbon dioxide, because it is a byproduct of the burning of fossil fuels, and we extract fossil fuels from the earth by the gigaton. So these are obviously the ones we pay the most attention to, although there's going to be 2 or 3 other gases that we're also very interested in this course. When you take a look at this here about carbon dioxide concentration, it's hard to be a good student in the environmental sciences and not know things like, what is the current concentration of carbon dioxide in the atmosphere? It's like 400 parts per million. What are the units? Parts per million. Why is it increasing? We kind of answered that already. You can see a diagram like this and see how there's all these trends and so on. What are some of the main anthropogenic sources of carbon dioxide? We're going to talk more later in the semester about like the carbon cycle in particular, but I mean these are just because I got them from the EPA website. We are talking explicitly about, like, in the United States, what are our contributions to carbon dioxide in the atmosphere. You can see the single largest source is the production of electricity at the present time. Transportation is a large source too. That's actually interesting to me as a teacher, because I know, like, in some textbooks, transportation was actually larger than production of electricity. I think it's just because of the improvements in fuel efficiency in recent decades that now actually a production of electricity is higher. Of course, it's also the larger demand for electricity, but that's another story. Anyway, so kind of having a sense of what are some of the key sources of anthropogenic carbon dioxide. We also talked about methane for a little bit. Methane has a much lower concentration. I mean, it's parts per billion. But each individual methane molecule is considerably more efficient as a greenhouse gas than carbon dioxide. So even though these numbers are, a couple of orders of magnitude smaller, that doesn't change the fact that methane is extremely important and comes from many anthropogenic sources. At the present time in the United States, the single largest source of methane is actually the natural gas industry. Methane is natural gas. That's what you're burning in your hot water heater or your stove if you have a gas stove. But natural gas doesn't mean it's good, okay? Natural gas in general is cleaner than coal or gasoline or something like that, but it still has plenty of problems, and part of the problem is just how leaky the natural gas delivery system is. From extracting it from the ground to delivering it to the consumer, there are lots of leaks in the system that are not cost-effective to run down. Natural gas is pretty cheap, so it isn't really in your power company's best interest to go around looking for every little leak in every little pipe. And it's just the cost of doing business. Oh, that's a problem. Nitrous oxides, that was another important greenhouse gas in the Earth's atmosphere. Know some of the basic sources. Notice, for example, that the single largest anthropogenic source of nitrous oxides are actually soil management. There are fertilizers and so on that then result in nitrous oxides in the atmosphere. On that day, Lecture 1C, we also were talking about this idea of trying to attribute extreme weather events to climate change. Everybody wants to do that. They want to be able to say, oh my gosh, this hurricane was due to global warming, or this drought was due to global warming, or whatever. But that's a really risky proposition. It is really difficult to attribute an individual extreme event to the broad global trend of increasing temperatures. And by all means, review that lecture to remember why, when we worked through why that's not something that you can really do here. But what we found is it was so much more meaningful to look for what seems like small temperature trends, but global, compared to like a heat wave. Okay, a heat wave on the eastern United States is important for lots of reasons, but it isn't necessarily a very compelling reason to believe in global warming. On the other hand, a temperature trend like this that is global, even though it may only be 1 degree Celsius per century or something like that, is a much more compelling reason to believe in global warming. And again, we worked through all of that stuff in the semester, in that lecture 1C. But we did find that while you can't really attribute individual extreme weather events, like an individual drought or an individual snowstorm, to global warming, it's actually not the end of the world to start talking about like the frequency of such events. The frequency of such events, remember, was determined by the probability density function, the PDF, that represents this sort of, bell curve, and the area under the curve, out in the tails of the curve distribution, is a measure. It reflects the probability that those events will happen any given year or whatever. And as we change slightly the distribution, if we shift the probability density function slightly to the left or the right due to global warming, or we make the tails fatter, or if we make the tails narrower, we get significantly different likelihoods of extreme events. And we walked through all of that back in lecture 1C, and I invite you to do that again. And of course, if you have any questions, please let me know before you take exam number 1. But we found that it's not tremendously difficult to show that you're going to have more heat waves in a world that's affected by global warming. And you'll find that it isn't the case that there'll be more extremes on both ends. I know that's often something the public thinks, that somehow there'll be more cold events and more warm events. That isn't the way it ends up working. It ends up meaning that there's not a greatly different number of the cold events, and there's many more of the warm events. Alright. This all works for things like the temperature record or precipitation records or something like that, because, we have so much of that data. There's thousands of weather stations observing every hour. If you want to talk about heat waves that are well observed by all of these stations, or you want to talk about occurrences of blizzards or something like that, where there's multiple events per year observed by many, many stations, that's not the end of the world to talk about its distribution. What proves to be hard, which is unfortunate because that's what people want, but what proves to be hard is attributing rare events to global change. Like, for example, the occurrence of hurricanes. Okay? The sample size is simply too small. We don't have the ability to attribute climate change as being the reason for a particular hurricane, or even the changes in the frequency of hurricanes. The truth is that is a very difficult thing to do in any robust scientific kind of way. Alright, then we moved on to lecture 1D, which was all about temperature in the Earth's atmosphere. And, well, first off, we spent a couple slides talking about why is temperature our preferred way. I know, you're thinking, but we're talking about global warming. Of course, temperature would be what we... Yeah, but that's not the title of the class. The class is actually about physical climatology and climate change. It might not immediately be obvious why temperature is the one we focus on versus pressure or cloud cover or something like that. But temperature turns out to be the quantity most directly affected by changes in greenhouse gases. It is the quantity that is easiest to measure. It is the one we have the longest record of. There were 4 or 5 of those kinds of reasons, okay, of why we thought of temperature as being our best way of describing climate change. And we talked about the fact that there are different systems for measuring temperature, or at least coming up with estimates of the temperature. Strictly speaking, they're always just an estimate. One was the in situ observations that come from things like thermometers, where the instrument doing the measuring is actually touching what it measures. And that was in contrast to the remote sensing observing networks. There were things like satellites. All right, we'll talk a little bit more about how satellites do that in just a little bit, but first let's talk about the in situ networks and how, like for example in the United States, we have a rather extensive network of unmanned weather stations, typically co-located with airports and run by the National Weather Service and the FAA. And they take hourly observations of temperature, wind, visibility, rainfall rate, all that kind of good stuff. Okay? They are there for congressionally mandated reasons associated with aviation safety and monitoring conditions for agricultural purposes and public safety and forecasting and so on. And that's different from the, just to give you a sense, those official National Weather Service, FAA type stations. There's about 40 in Nebraska, somewhere in that ballpark, maybe 30. In contrast, there's about 600 in Nebraska of these cooperative weather stations that are actually run by volunteers. They get some kind of like online training or whatever, and then they get special equipment to put in their yard where they are measuring daily values, daily precipitation total, daily high temperature, daily low temperature, etc. It's a type of climate modeling, but it's much less expensive. I think nowadays it is actually done like in real time, like the information gets relayed over a network, you know, each day. Historically, it was done like they actually wrote the precipitation down on a card or the high temperature on that card, and when like after a month when the card was full, they literally would mail it in. So it wasn't really such a real-time kind of thing. It was more of a climate studies kind of thing. But this is another very large network that we have in the United States. And to be honest, most countries have something kind of like this. Kind of a two-layered strategy for measuring their weather and climate. Typically, they have official government-mandated observations at, typically mainly at airports, and then some kind of secondary network that kind of provides an independent layer of information as well. At sea, I mean, this is all really well and good at sea. I think even a relatively poor country can afford thermometers and rain gauges and stuff like that. The question is, what are you going to do at sea, which covers 70% of the Earth's surface? Well, we learned about the fact there's different kinds of buoys out there that monitor the climate. We talked about the fact that there are observations that come in from merchants at sea. This is all important in terms of how we monitor the climate at sea. We have to be careful when we're working with all these data because there can be inhomogeneities. I don't want to get in the business right now of reteaching the whole story of inhomogeneities in a long data set. If you need to go back into Lecture 1D and look at that stuff, great. But we talked about the nature of what is an inhomogeneity and what kind of problems it can cause and stuff like that. Make sure you know about that. Okay? If something were to change, if an airport is closed down and moved and we take the weather station with it to a new location, that's an inhomogeneity in the data set. If the airport used to be 10 miles outside of the city in a very rural environment, and now that the city has grown and now that is in a very urban environment, that's an inhomogeneity. And there are ways to fix that, but we got to know about it. We talked about remote sensing of temperature and how it's kind of an extension of the kinds of things you learned in ATS 113 about like the Stefan Boltzmann law, okay, where like the amount of long-wave radiation an object is emitting depends on its temperature. So if we take the ground or the surface of the ocean and we look at it with a imager on a satellite that can measure the amount of long-wave radiation coming up from that surface, that ocean or whatever, we can do the calculation and determine what the temperature of that object had to be. This is a complicated story. Okay, anytime you're using remote sensing techniques, it becomes really complicated really fast, but the basic idea is solid. Okay, how to recover, the right word is actually retrieve, the temperature based on the amount of radiation that reaches a satellite. And with all these data in hand, we were able to start doing things like talking about, ballpark figure, how much has the temperature of the Earth increased over the last 100, 120 years or whatever? Where has it been warming? It's not an even amount. How much more has it been warming in the Arctic than in the tropical latitudes, etc.? Do the satellites agree with this assessment during the period since about 1979 when we have satellite data? Do the satellite data agree? Is that important? Yes, it is important. It's another independent source of information, right? The satellite does not know what the thermometer is seeing, so that is two separate pieces of information trying to determine the temperature at a location. With that information in hand, we went on to Lecture 1E. Now, in Lecture 1E, we started saying, temperature is not the only thing that matters here. Changing the temperature might result in changes in weather patterns, might make changes in humidity, might make changes in the winds, I mean, who knows, right? And because in terms of the human experience of climate, the hydrologic cycle is so important, we spend more time on the hydrologic cycle than anything else. about, like precipitation and groundwater and runoff and so on as different ways of understanding, well, what could change and what is changing. I guess at this point we're mainly working with observations. What is changing? Now what we found, of course, was when we did this hydrologic cycle is a lot of the things that would be really interesting if they were making a big change aren't making statistically significant changes at the present time. For example, runoff. It would be really interesting if there was an increase in runoff associated with global warming. And it's altogether possible that that is happening, but the statistics don't show it yet in a statistically significant way. Okay, well that's something, if I'm a policymaker, I need to know that. I need that information. It makes sense. But on the other hand, like for example, precipitation. Man, everybody would be very, very well served if we had a definitive answer about how precipitation has changed over the last 120 years in terms of global warming. Now, at a very abstract level, it makes sense that there should be some connection between precipitation and global warming. A warmer world should be a rainier world because we have a warmer world means more evaporation. Hey, we gotta sort that stuff out first. Remember, a warmer world means a world with more evaporation. Evaporation is actually controlled by a number of factors, but one of the most important is temperature. So a world where it is warmer means that there is more water vapor going into the atmosphere. Well, the atmosphere doesn't store the water vapor for long periods of time. The residence time of the water vapor is only a few days. So in relatively little time on the comparison to climate, that water vapor gets turned back into rain and jumps on the ground. So, even on the scale of a few days, globally, the amount of evaporation has to equal the amount of precipitation. So if by Clausius-Clapeyron equation, you know that there must be, well, there's more, a warmer atmosphere can hold more water vapor, so there must be more evaporation. Well, if there's more evaporation, there apparently is more precipitation. So it makes sense in kind of an abstract sort of way, in a theoretical kind of way, that a warmer world should have more precipitation. By the way, make sure you do understand this graph of the Clausius-Clapeyron equation. Again, I'm unlikely to just give you a simple little problem like you might have had at ATS 113 where you read numbers off of here, but knowing what the graph means might be important on this test. So does this work? Does our warmer world show more precipitation? Well, the answer turned out to be kind of unsatisfying. I mean, globally, when you used 4 different global data sets of precipitation, they generally showed statistically significant trends globally. Which sounds like a good answer, but statistically significant and clear or important aren't always the same thing, and this is a good example of that. These trends, these global trends of precipitation, while statistically significant, are pretty small. I mean, this is definitely not radically changing the hydrologic cycle with these results. There is a small upward trend, though, globally, but if we start busting that out into different latitude bands, like, for example, if we just want to look at the high latitudes, which is where our greatest temperature changes were happening, what we find out is there's definitely a much larger precipitation trend in the Arctic than there is globally. Oh, okay, well, that's probably not a huge surprise. I mean, the Arctic also is warming a great deal more than the globe is on average. Okay. Whereas, for example, we could do the same sort of calculation and look at just the tropics. Is there more precipitation in the tropics now than there was 120 years ago or something like that? And all data sets say, no, there isn't. Well, I take it back. They don't say that there isn't a trend. They say they can't prove that there is a trend. Okay, that's what statistically significant means. There aren't statistically significant results for the tropics. We can't yet prove conclusively that there is a trend. Whatever trend there is there so far is small. Excuse me. All right. So we have some possibility of these trends, but keep in mind that the results are going to be very regional. Excuse me. For example, there has been a marked drying trend in West Africa. There has been a marked moistening of the climate across the central parts of North America. Okay, it's all very variable regionally. Okay? But broadly, we can say that whatever precipitation trend is happening, it's clearly stronger the farther you get away from the equator. Okay. Hey, if you want to wind back here for a second, I mean, people don't tend to think too much about humidity, but that was kind of closer to the root of the problem here, wasn't it? I mean, Clausius-Clapeyron equation says that a the amount of water vapor the atmosphere can hold depends on the temperature. And we know the temperature is changing, so the amount of water vapor the atmosphere could hold is changing. And in fact, we do observe that near the surface anyway. Near the surface, pretty much worldwide, we're seeing that the atmosphere is holding more water vapor than it was holding, 50 years ago, 100 years ago, whatever. That's interesting. We see that from in situ data sets, we see that from remote sensing techniques. There are remote sensing techniques to measure the water vapor in the atmosphere and so on. We actually saw, by the way, that this is mainly true at the surface. Aloft, where rising and sinking motion has more to do with the amount of water vapor in the atmosphere, it got complicated fast. Another change that we might expect associated with global warming might be a change in the amount of cloud cover. I mean, I diligently tell ATS 113 students that this could be a big problem. Because we don't even know yet for sure, at least not at this point in your education, but we'll get there, what is the role of clouds in the atmosphere? I mean, are clouds reflecting more sunlight away from the Earth and they help keep the Earth cool? Or because clouds are made of liquid water droplets and therefore they act to enhance the greenhouse effect, are clouds keeping the Earth warm? But we really at first at least need to know if there's more clouds or fewer clouds. And theory tells us that there should be more clouds, but in practice, we don't actually see that yet. Our satellite archives of clouds cover are just not that good yet. They're not that long. And surface-based observations of clouds from observers are terrible. They have huge inhomogeneities. The same reporter will report different amounts of clouds. Two different observers standing near each other will report radically different amounts of clouds. Cloud is just really hard to measure. So we don't really have any good results to tell about that yet. And then that lecture kind of boils over, or spills over a little bit to 1F, where we start saying, well, what about weather patterns associated with all of this? How is the climate changing what we expect in different parts of the world? You might remember that one thing that theory was telling us is an expectation that the tropics, the area of the globe that is experiencing tropical weather, if you're a survivor of the tropical meteorology class, you know I'm talking about things like trade winds and the Hadley circulation and so on, that by various measures that should be increasing. And in fact, that is what we are seeing. This particular slide, you'd have to go back into the IPCC report to remember exactly what's going on here. But this diagram here shows different definitions of the width of the tropics over the last 35 years or something like that. And by all those definitions, it's clear that the tropics are getting wider. Okay, that pushes all the other climate zones closer to the poles as well. For example, the storm track. Okay, the storm track is the pattern that mid-latitude cyclones and anticyclones tend to follow. They don't all follow exactly the same path, of course. That would make forecasting too easy. But they do, averaged over the course of the year, typically have a typical path that is called the storm track. And the storm track does seem to be getting pushed farther north too, which changes the distribution of precipitation and changes the distribution of severe weather, and could all be very important to the people living in different regions. Then we moved on and started talking about ocean stuff. Okay, the beginning of that lecture was just talking about water temperature. Okay, sea surface temperature, temperature of the upper 700 meters of the ocean, etc. And it's not exactly rocket science. It got warmer, okay? We learned a little bit about how we measure it and things like that. But basically, okay, it's warmer. And that's important, and that has a story to tell us later in the semester about ocean acidification and things like that. It can result in changes in ocean currents and so on. But the real thing I want you to know at Module 1 of the course is how that relates to sea level change. Because sea level change is a very hot topic, no pun intended, and for the public's point of view and funding agencies' point of view and so on. And it turned out there are two main ways in which the sea level height is changing. One had to do with the melting of grounded ice. Make sure you know that term, grounded ice. And also the thermal expansion of seawater, which probably you found shocking. Because you don't expect water to have much of a thermal expansion. The coefficient of thermal expansion for water is very, very small. Just a tiny fraction of 1%. But when that heating is happening over a very thick layer of the ocean, like a 700 meter thick layer, the resulting expansion of the ocean could be as much as a few centimeters. And so, we are getting, from observations using tidal gauges and things like that, globally averaged increases in sea level height of about, I hate the fact that this diagram does it in inches, but whatever, maybe 10 inches, 9, 10 inches, something like that, over the last 100, 120 years, something like that. Wow, that's a lot of increase in sea level height. Then we went on to cryosphere stuff. I mean, the ocean, climate change in oceans could be a whole course. Let's talk about cryosphere stuff. Now, you need to sort out, make sure you're clear about the difference between glaciers, sea ice, and ice caps. Okay? Because using the wrong word for that is, it's one of the things I have to take off for. Okay? When I'm grading your test, I have to be watching for, like, oh my goodness, this person said that ice caps are retreating, but it's glaciers that are retreating. Okay? I mean, you have to be clear about that. Okay. So make sure you have those three terms sorted out. And I thought one of the most important things when I was reviewing this was this business of how we see worldwide nearly all glaciers are getting shorter. What's the connection between that and global warming, however? Lots of local factors affect the length of a glacier, like precipitation and cloud cover and so on. Why are we blaming this on global warming? Remember, the argument was it would be very strange if all these glaciers are all getting shorter, but for all different reasons. It seems like there would be some getting longer and some getting shorter. That is the way it works. They're all getting shorter, so it must be a global reason. Let me give you an analogy. My oldest son's in first grade. If all the first graders are gone on one day, they're homesick, it could very well be that this kid's got chickenpox, and this kid's got strep, and this kid's got the flu, and this kid's got a cold, and this kid's got diarrhea, whatever else, okay? But when it would be weird that they'd all have something different. A much better explanation as to why they would all be sick on the same day would be some kind of global condition, like global as in across the whole class. Like, they are all home with strep because one kid came to school and gave them all strep. He came to school sick and he gave them all strep. It would be weird if each one of them had its own reason why it happened and they just all happened the same way. Okay, the global explanation just makes more sense. We talked about sea ice. Make sure you know, like, the annual cycle of sea ice. When is the most sea ice seen in the Arctic Ocean? When is the least? How is that related to sensible heat flux between the ocean and the atmosphere? Ice sheets. We all know that, especially in Greenland, the ice sheets are melting. Hey, how do we know that, though? Remember about this business of tracking their mass using gravity and so on? That was all pretty straightforward. Again, we could have a whole course in climate change and cryosphere stuff. We don't. Okay, we're going to just sort of use this as a tool to talk about other aspects of climate and climate change. At which point in the IPCC report, they switched to the topic of paleoclimate. As, paleoclimate, the climates of the past, paleoclimatology, studying the climates of the past, etc. And what kinds of data are available to you to study the climate of the past kind of depends on how far back you want to go. We talked about, like, for example, the satellite record. The satellite record only really goes back to about 1979. That's really when we got good at storing data, okay, in ways that we can permanently access and so on. Prior to that, the satellite data tended to not be archived, or archived in formats we don't know how to work with anymore. It just didn't really, or the satellites had calibration problems, and so we don't tend to have it farther back. 1979 is not exactly terribly far back. On the other hand, it might be long enough to have, that's, got maybe 30 years of data or something. You might be able to see climate trends and so on. But that is different than, like, the instrumental record, which is, literally how long we've been running weather stations. Most developed nations got their weather stations going like in the 1860s, 1880s, something like that. Although some, especially in the colonial era, did extend back to literally like the 1700s or earlier. And some of those observations are really quite good and well calibrated. But, at best we're talking a couple hundred years so we can go back with this kind of observation. If what you mean by the climate of the past is only that far back, that's no problem. We can go back with historical records and recreate the climate of the past if we have some kind of historical information. You might remember, like, South American missionaries kept records of their harvests back to the early 1500s. Well, from our knowledge of what they were growing and so on, we can figure out what amount of rainfall they must have gotten. Sometimes they actually even recorded the rainfall. You might remember the Nilometer, which was, a way of measuring the height of the Nile River, which is another way of basically saying the integrated rainfall upstream from the Nilometer. Makes sense. Even that, though, we're talking at most a few centuries to 1,000 years. I think the Nilometer goes back to like the 600 AD era, with some records, some less well-calibrated Nilometers going back a few hundred years before that. But we're still not exactly talking the ice ages, right? Okay? If we want to go farther back than that, we got to talk about paleoproxies, where you have these long-lived chemical, biological markers for the climate information. Like in ice cores, where we go out onto an ice sheet or onto a glacier and extract a core of ice and are very careful not to contaminate it and all that kind of good stuff. And from that climate, we can get all kinds of climate information from these ice cores, where we can actually, find layers in the ice that correspond to years. They might be a specific year, like as in we can find volcanic dust from a known volcanic eruption in a particular year, although more often it's more a matter of we can see almost like tree rings. We can see individual layers in the ice core that correspond to years. We don't know exactly what year each one of them is, but we can see the structure of how things varied over a period of years. Usually that annual structure is revealed by the presence of dust in the ice. Typically, like on a glacier, for example, typically during the winter, the area around the glacier is covered with snow, so there isn't really any dust being transported onto the ice. And then during the summer, the area around the glacier becomes snow-free, and dusts from the surface soils transport onto the ice sheet. And then in the next winter, of course, again, it deposits clearer ice. So we can at least see this sort of annual structure to the ice, and we can do things like extract little bubbles that are trapped in the ice. And from that, we can actually get things like the carbon dioxide concentrations in the atmosphere. Now, the oldest ices on the Earth are about 800,000 years old. Any ice that's older than that has long since been pushed, melted or pushed out into the sea, become an iceberg, and eventually melted or whatever. 800,000 years is a long time, though. And what we know is there's been no time during the last 800,000 years where carbon dioxide concentrations were as high as they are now. Okay, that's valuable information, okay? What else can we do? We can actually use the water in the ice itself to infer something about global sea surface temperatures. Remember, the water molecules that are that ice contain an oxygen atom, and that oxygen atom can be one of two different isotopes. Oxygen 16 and oxygen 18. The rate at which water with an oxygen 16 atom evaporates is different from the rate at which water with an oxygen 18 atom evaporates. And the difference between those two evaporation rates depends on the temperature of the water itself. So if you have a layer of ice in your ice core that is relatively enriched in oxygen 18, you know something about the water temperatures, at least the water temperatures where that water evaporated off of the ocean or whatever. And if you have water that's, if the ice is relatively enriched in oxygen 16, you know something else. You know the opposite about the temperatures there. So that makes some measure of sense as to how we can just recover that climate signal through this paleoproxy. We have other paleoproxies too. We didn't get all bogged down, but I mean, there's all kinds of ways you can use dendrochronology, the study of tree rings. Generally speaking, these tree rings, most trees live where their growth each year is limited by at most one phenomenon, like rainfall rate. Like it's plenty warm, but it's just whether they get enough rain. How much rain decides how much they grow. Or maybe there's plenty of rain, but if the weather isn't warm enough, they don't grow very much. I don't know, just by looking at any given tree, what the hell's going on, but I'm not an arborist or, any kind of botanist or anything like that. Someone else can tell you that. They can tell you that in central California, the growth of oak trees is limited by temperature, let's just say, or more by moisture or something. And so from the width then of these tree rings, we can recover a climate piece of information. And with records like these, we can start finding out things about the climate of the last few thousand years, the last few 10,000 years, etc. Make sure you know about some of these terms. I mean, it's hard to be an environmental science major and not at least have something to say about things like the medieval warm period or the Little Ice Age. Okay, if you're an environmental science major and you get the Little Ice Age and the Ice Age turned around, you got a problem. Okay, make sure you know about when those things happened and so on and their relative difference. Then we looked at like climate change over the last, say, 15,000 years or so, and you can really see how there are stadials and interstadials. Make sure you know the difference between those two. You can see the Holocene warm epoch there. Ice ages, the most recent ice age, which was a bit of a doozy, was about, it reached its peak about 25,000 years ago. Ice ages tend to last a few tens of thousands of years, and there are interglacial periods between them. And when you start looking at reconstructions of climate over the last, 4 million years or something like that, you can see that there is there have been literally dozens of ice ages just in the last few million years. There have been literally hundreds of ice ages in Earth's history. And a big part of that story is a natural form of climate variability associated with the so-called Milankovitch cycles. Remember the Milankovitch cycles? This was this business of how the orbit of the Earth becomes either more round or more oval over periods of like tens of thousands of years. The right word is it becomes more or less eccentric. And you should know that story about why changes in the eccentricity of the orbit end up resulting in climate change. I mean, as the orbit of the Earth gets more eccentric, there are times when the Earth is closer to the Sun than it is now. There are times each year where the Earth is farther from the Sun than it is now. So why does becoming more eccentric mean that the temperature of the Earth is going to be colder? You're going to need to make sure you review that. And if you have any questions, let me know. I want to get that sorted out with you. All right. What else we got here? Solar output. I'm not going to have tons of stuff on this test about solar output. That's not the most important thing to me. Yes, there is some variability of the amount of energy that the sun puts out. And there are people who are going to tell you that climate change is not caused by man, it is caused by natural solar variability. And what we did is worked our way through the argument in that class that shows, no, that isn't how it works at all. I mean, obviously, yes, on very long time scales, like, over the course of geologic history on the Earth, since the last billion years or so, the sun has increased in its luminosity by about 30%. That's just part of being a main sequence star. Yes, we have had periods where the Earth was much colder. We had periods, yes, on very long time scales, the temperature of the Earth does track the solar output. But the very small changes that happen that are quickly canceled out by small changes the other way due to things like sunspot cycles and stuff like that don't have anything to do with climate change. Okay, so I don't want to get just too bogged down about that. Then we had a handful of slides at the end of the presentation 1G that were about what do we actually learn about the Earth's climate from paleoclimate studies. How do we know how the present climate is different compared to climates of the past? And again, there's a handful of slides here. Is the Earth warmer now than it's ever been? No. Etc. There's like 3 or 4 slides with the kind of results. Okay, and that's it. That's all. When I went through the 6 different presentations this morning, looking through here, that's what I thought was the most important sets of things to know about. All right. Now again, like I said, I didn't look at the test when I made this presentation. Okay, I'm not saying everything that's on the test is on here. It would be a good use of your time to go and spend some time with the with the review sheet and so on. And of course, let me know if you have any questions before you take the test.